So this video covers how to monitor the rate of a chemical reaction. So in these past few videos we've had a look at concentration and pressure, surface area, temperature and catalysts. In this one I'll show you how to monitor the rate of a chemical reaction. Now it's important we know how to monitor the rate of a reaction that produces a gas and how to monitor the rate of a reaction that produces a solid. And we can do this in several different ways. So we could start off with a really simple reaction, like the reaction of magnesium metal and dilute hydrochloric acid. So the bubbles in the test tube, of course, are hydrogen gas. Now, if you react the magnesium with an excess of hydrochloric acid, that means too much hydrochloric acid, the reaction will stop when the magnesium runs out. So you could drop the magnesium metal into the hydrochloric acid, start your stopwatch straight away, and you could stop your stopwatch when there's no more magnesium left. If you did it the other way round, if you had an excess of magnesium, the reaction would finish when the hydrochloric acid ran out. So you could drop your magnesium into the hydrochloric acid, start your stopwatch, and then stop your stopwatch when there was some magnesium left but there were no more bubbles of hydrochloric acid. Now you could use a reaction like this to investigate concentration of hydrochloric acid or indeed temperature of hydrochloric acid. You could also do surface area of magnesium. The important thing is every time you repeat the experiment you will end up with a time in seconds for the reaction to finish. Now times and rates work in opposites. If the time is very short, the rate of the reaction will be high. And if it takes a long time for the reaction to finish, the rate of reaction would be very low. Now, when you get a time in seconds, you can do the following. You can put the number 1 in your calculator and divide it by the time in seconds. Now that could give you a very small number, so what you could then do is multiply that by 1,000. And that will give you a value that is proportional to the rate of reaction. Now, if you're investigating concentration of hydrochloric acid, you would do this reaction perhaps 5 times with 5 different concentrations of hydrochloric acid. Really important, the mass and the surface area of magnesium is the same each time. The volume of hydrochloric acid is the same, and the temperature of hydrochloric acid is the same. So the only thing that you're altering, the independent variable, is the concentration of hydrochloric acid. Your dependent variable would be the time it takes the reaction to finish. Let's move on to another example. Now in this reaction here, we could have calcium carbonate chips, otherwise known as limestone, with hydrochloric acid. So I'll label this and I'll do an equation. So as the reaction proceeds, we get bubbles of carbon dioxide gas. The pieces of calcium carbonate will get smaller because the product that's produced, the calcium chloride, is soluble in water. Now you'll notice that I've done this reaction on the top of what we call a top pan balance. And that's because carbon dioxide is a gas that's quite dense, but it can escape through the cotton wool plug in the mouth of the conical flask. Now, a cotton wool plug will let gases escape, but it will prevent drops of hydrochloric acid splashing out. Now the reading on the top pan balance will go down as the carbon dioxide escapes. And you could plot a graph of the mass of carbon dioxide lost against time, and you could use that to work out your rate of reaction. Quite a bit more about that in the final video when we look at graphs. Now it's important not to use this method for a reaction that produces hydrogen. Hydrogen's got the lowest density of any gas at all, and you would have to have a very, very precise top pan balance to record any loss in mass at all. This is suitable for a chemical reaction like the one in the example that produces a dense gas like carbon dioxide. So for a reaction like this, you would plot the volume of gas lost against time. You'd record it every 30 seconds, something like that, and you'd end up with a graph that looks like this. Now, the rate of reaction is continually changing. It starts off very quickly, then it gets slower and slower and slower, and when the graph gets parallel to the x-axis, the reaction has stopped because one of the reactants has run out. Now, the reason why this chemical reaction starts off really quickly and then slows down is that the hydrochloric acid is at its most concentrated at the start, and every time there's a collision, the concentration of hydrochloric acid reduces, there are fewer particles per unit volume, and therefore fewer collisions per unit time. Now, another way you could monitor the rate of reaction that produces a gas would be to connect this apparatus up to a gas syringe. So in this example, let's have a look at the reaction of zinc metal and dilute hydrochloric acid. Now, in this reaction, it doesn't matter that the hydrogens are really low density. Simply what you can do is you can read off the volume of hydrogen gas produced every 30 seconds, and you can plot a graph of hydrogen gas produced against time. So what you do is you would pour your hydrochloric acid into your conical flask, you would add the zinc, and then as quickly as you possibly can, connect the apparatus up so you lose as little hydrogen as possible, and then start your stopwatch. That is another variation of the same thing. You could do your reaction in a conical flask, connect the apparatus up, and then you could collect the gas in an upturned measuring cylinder. You'd collect the gas by bubbling it through water, and you'd make sure your measuring cylinder was full of water first, because the gas, of course, will rise up to the top of the tube and it will force the level of the water down that way. So what you can do in this situation is record the volume of gas produced every 30 seconds and once again plot a graph of volume of gas against time. Now, a couple of problems with this method. Number one, I suppose it can be quite tricky to read the volume of an upturned measuring cylinder. But number two, if the gas dissolves in water, and remember you're bubbling it through water, then you're going to lose quite a bit of gas because it will dissolve in the water. So that's why you would never use this method for a reaction that produced a really soluble gas like ammonia or hydrogen chloride gas, for example. Now, you might wish to monitor the rate of a reaction that produces a solid. So let's have a look at an example here. Okay, so if we have a look at this example, this stuff here is called sodium thiosulfate, and it reacts with dilute hydrochloric acid, producing a solution of sodium chloride. So that AQ means a solution. We get water, we get sulfur dioxide gas, but we get sulfur, which is a solid. So that's our solid product, and we would therefore call this a precipitation reaction. So if I mix sodium thiosulfate and hydrochloric acid together, and if I watch this from the top of the conical flask, what's going to happen is the mixture is going to get cloudier and cloudier and cloudier until I can no longer see through it. That is why we do this reaction with a cross on a piece of paper below it. We would then pour one solution in, for example the sodium thiosulfate. You'd pour in the hydrochloric acid, you'd give it a quick swirl, and you'd start your stopwatch. You would then stop your stopwatch when the mixture has got so cloudy you cannot see the cross underneath the conical flask anymore. And you could use this reaction to see how the concentration of either solution affected the rate of reaction, or to see how the temperature affected the rate of reaction. Your results in this case would be times, probably in seconds, for how long it takes the mixture to become so cloudy you can no longer see the cross underneath it. So what you do, as we've done before, is you'd work out the rate of reaction by doing 1 divided by the time in seconds multiplied by 1,000. Okay, so there you go. Right, so that's rates of reaction, so how to monitor the rate of reaction, hopefully made simple. Thanks for watching.